Hey, welcome to The Explainer. This is where we take big, complicated topics and, make them make sense. So let me ask you something. Can a map lie to you? I mean, we see them constantly, right? In the news, on websites, these colorful maps showing disease outbreaks or maybe crime hotspots. And our first instinct? We trust them. But what if I told you that the way these maps are often put together can be, well, dangerously misleading? Yeah, take a look at this. A map that just shows you the raw numbers. It might not be telling you the whole story at all. So today, we're going to decode what's really happening behind all those colors and find out why this stuff matters. A lot. Okay, so the absolute biggest issue comes down to something that statisticians call the small number problem. Just think about it. You've got an area with a really small population. All it takes is one or two random cases of something, a disease, a crime, and suddenly the rate for that area just skyrockets. It creates all this statistical noise that can make a perfectly quiet, safe place look like a total crisis zone, just by pure chance. And this chart? It shows the problem perfectly. Look over on the left. See how the data points for areas with small populations are just all over the place? Totally unpredictable. But then, look to the right. As the population gets bigger, the rates get much, much more stable. They're more reliable. So how in the world do we fix this mess? Well, the answer is pretty cool, actually. It's all about learning to think like a spatial analyst and getting a grip on a really core principle of geographic data. It's this idea of spatial dependence. It sounds complicated, but it's not. It's this simple but super powerful idea that things that are close to each other tend to be more similar than things that are far apart. Think about house prices or even the weather. What's happening in your neighbor's yard is usually a pretty good clue about what's happening in yours, right? That clustering is a massive feature of this kind of data. And this visual just illustrates it perfectly. That pattern on the left, the one with all the clustering, that's what we see all the time in real-world data, especially with health and social issues. If you ignore that fact, you are pretty much guaranteed to come to some flawed conclusions. Okay, so now that we get that, the very first step to fixing our map is a big one. We have to stop using raw counts, period. Instead, we need to start using rates, but not just any rates. Rates that are properly adjusted to deal with those population differences we've been talking about. And that brings us to the difference between a crude rate and a standardized rate. Think of a crude rate like a sledgehammer. It's simple, yeah, but it's a blunt instrument. A standardized rate, on the other hand, is like a surgeon's scalpel. It's a precision tool, and it's absolutely essential if you want to get an accurate picture of what's going on. And this quote right here, it really gets to the heart of the matter. It says that rates for areas with small populations, small denominators, just have way more variance. They're way more unstable. Standardization is what helps us control for that wild instability we saw in that chart a minute ago. So how does this whole standardization thing actually work? Well, it's a logical process. First, you start with what you actually see, the observed counts in each area. Then you bring in the population data, stuff like the age breakdown. Step 3 is where the magic happens. You create an expected count. This is basically asking, how many cases should we see here if this area behaved like the national average? And finally, you just compare the two, what you actually saw versus what you expected to see. That gives you a standardized ratio, and it answers the most important question. Is this area seeing more or fewer cases than we'd expect once we account for its unique population? All right, now for the big payoff. Let's see what happens when we actually apply all of this to a map and reveal what's really going on. Okay, look at this simple table. We've got two neighborhoods, A and B. Both have 10 cases of a disease. But neighborhood A has 1,000 people, while neighborhood B only has 100. So if you just calculate the crude rate, whoa, neighborhood B looks like it has a problem that is 10 times worse than neighborhood A. But wait a second, what if neighborhood B just happens to have a much older population, and what if older people are just more likely to get this disease? See, that's exactly the kind of hidden detail that standardization is built to fix. And here it is. This is the difference it makes. On the left, you've got the map based on those crude rates. It looks chaotic, right? Alarming. It's totally driven by that small number problem. But then look at the map on the right. The standardized map completely smooths out all that statistical noise, and it reveals the true underlying pattern of risk. So why does any of this matter? Because getting the map right has huge real-world consequences. We're talking about where public health officials decide to send resources, right? Where to allocate funding. An accurate map lets them pinpoint the real hotspots, not just the statistical flukes. It helps them avoid causing a ton of unnecessary public alarm. This isn't just an academic exercise, not at all. It's about making sure help gets to where it's actually needed. Yeah, at the end of the day, a good map does way more than just show you some numbers. It tells a much more robust and reliable story. It makes sure that the values we're comparing are, as the experts say, equally robust. So, if a simple map can be this misleading, it kind of makes you wonder, what other charts and graphs should we be questioning? The next time you see a data visualization, I want you to ask yourself, what's the denominator here? What context could be missing? Because asking those questions, well, that's how you go from being just a passive observer to a really informed analyst.